All right. Thank you. We're going to move to the final speaker of this session. And so we will next be hearing from Zain Kamal, who will be talking to us about impact-induced demagnetization in the Martian crust using high-resolution MAVEN data.
Hi everyone, I'm Zain. My presentation is on impact-induced demagnetization of Martian crust, like you saw. A QR code will be available again at the end. I'm happy to discuss, feedback, criticisms, all my code and data analysis over there as well. So yeah, we'll get into it. So my talk is roughly sequestered into 3 parts, introduction, methods, and future work, kind of all going on these 2 central questions of when did the Martian dynamo actually die, and what is the depth of magnetization in this Martian crust. So to start with introduction, we'll kind of talk with some motivations for studying crustal magnetization. And for more details, I highly recommend this review by Muehlholz and Johnson. So, as you all know, Martian dynamo is dead right now. Current measurements of this are from the MGS, MAVEN, and InSight spacecrafts. But before, we're fairly confident that about 4.0 gigaanoms ago, the dynamo was alive, possibly Earth-like at that time. And so the reason why we're looking at crustal magnetization, specifically through this lens of impacts, is that it gives us kind of these pictures, and I'll talk more about snapshots of the dynamo over time, and it'll also help us constrain the magnetization depth. And so I kind of have a cartoon example right here. Imagine we have like some, let's say, molten section of crust with those arrows representing the magnetization vectors. Right now, it's very demagnetized. In the presence of some active field or dynamo, the crust will be magnetized in some direction with the same wavelength and amplitude. And as this cools, this will be quote unquote set in stone, and it'll be preserved for a billion years, such that even if the dynamo weakens or completely flips direction, the reading is maintained. And so we could fast forward from the formation of the crust to an impact event. And if we pause during this moment, of course, the intense heating past the Curie point and the shockwave pressures will demagnetize this crust. And this is where that kind of snapshot euphemism comes into play, because we can talk, the crust is now susceptible to, if there is a background field, it will take on again that amplitude and direction, and again be set in stone. And this is measurable by spacecraft, either MAVEN or MGS, and indicates the field present at the time of the impact. And so this is partial an explanation of the mechanisms for the 4 major impact basins. Top is molar topography, bottom is magnetic field signatures, although there's also something to be said about excavation of the actual crust, although that's further. But we also want to consider a lot of the smaller craters, and that's the focus of my work, because the main thing we have to change in our approach is that we can't assume homogeneity of the crustal magnetization. And so this is kind of unsure, but we have 2 main hypotheses right now, either shallow or deep. And the reason why this is important is because both of these will react very different to impacts, where in shallow magnetization, that's going to demagnetize the upper thing, and we're going to have this differential in magnetization that's very easily measurable. Whereas for deep magnetization impacts, or impact-induced demagnetization, will largely be not noticeable. It seems like nothing has changed. And so to reiterate, the reason why we're looking at crustal magnetization through this lens of impact is to get kind of pictures of the dynamo over time to hopefully understand when it died, and also constrain the magnetization depths. And those are the 2 questions that we'll be answering. So now we can move on to discrepancies in past works. Again, we have these 2 questions of dynamo cessation timing and depth of magnetization. I'll talk about kind of papers in the past, search parameters that I've been using for impact-induced demagnetization, and the conclusions that I've come to. So a lot of older work with MGS data kind of calculated that the minimum diameter of impact craters in order to lead to demagnetization is roughly 300 kilometers. And anything bigger than that should be demagnetized. But when they looked with MGS data through about, I think it was really 23 craters, might be wrong on that, they found no notable magnetization signatures. And this suggested that the magnetization source was very deep, and it pegged a dynamo cessation estimate fairly early. But some more recent work by Muehlholz et al. In 2020, and a more recent work in PrEP, looked at MAVEN data. And this is important because it's much higher resolution. It's resolved at altitudes much lower, from 400 MGS to even low as 110 kilometers for MAVEN. And this specifically looked at the region of Lucus Planum. There's a picture right here, and this is important because a lot of pyroclastic flow in the region meant that if there was shallow magnetization of the crust, this would be very easily detectable right here. And so this is exactly what we found. On the left, we have these MAVEN tracks, which show very strong demagnetization, and that's reflected on the right of the magnetic field over here, dropping significantly. And this is roughly a 70-kilometer wide region. Just for modeling, kind of let's combine these craters together. And so there's some more work on this, but this suggests that the magnetization depth was fairly shallow, and a dynamo cessation estimate fairly off, but not off, different from before, and expanding as well. And so these are the two, again, questions that we're seeing a bit of disagreement on that I'd like to address with this work, mainly estimating the dynamo cessation by looking at a comprehensive look with MAVEN data, and the depth of magnetization and seeing if that's just natural processes or if there's something else more complicated involved. So to move on to my methods, specifically with my data, to kind of contrast with what came before, I'm taking a look at all impact craters on Mars greater than 70-kilometer diameter, and that leads to a sample size of about 855 craters, and I'm using night side MAVEN data at altitudes of either 170 or 200 kilometers. And just to summarize what we found, we're finding about 10% of craters, so 1 out of every 10, greater than 150 kilometers is demagnetized clearly. In the 70 to 150 range, that's either unresolved or we're really not noticing anything. But there's this work is still going on, and there's some interesting examples that we're really not sure about. So one of the main ones is this Henry crater, which is located in Arabia Terra. Again, no topography on the right, and on the left, on the right, we have these MAVEN tracks going over the crater. And to further analyze this, we have these cross-sectional plots, and I'll explain these more. First, for each plot, we'll have these 8 different colored line plots corresponding to the 8 MAVEN tracks that go over here. You can kind of see the 8 going to there. On the top right, we have altitude of the MAVEN satellite as it went over the crater. On the bottom, we have these spherical vector components, so radial, longitudinal, latitude of the magnetic field around that crater. Top left, we have magnitude of the magnetic field, and top middle, we have the same thing, magnitude, but normalized such that each track individually has a maximum at 1 and a minimum at 0. And hopefully you could see now, Henry crater, despite being less than that 300 kilometer minimum demagnetization estimate, it's only 170 kilometer diameter, sees about an 80 to 90% demagnetization. And to further back that up, these vectoral components all kind of flip-flop and pass through that 0 mark, which gives a strong confidence that this is a region of strong demagnetization. For reference, here's a similar sized null result of still 170 kilometer diameter that exhibits no demagnetization. And this is what a lot of the other craters on this range look like. So to kind of quantify this, we came up with a subjective kind of crater magnetization rating from -3 to +3, where something like Henry crater would fall into -3. The null result would be about 0. And another example I didn't show before, but strong remagnetization would go to a 3, and it's all the integers in between. So with this kind of approach in mind, we could start kind of coming up with an estimate for when the dynamo died. So we come up with a small subset of 17 craters from this set, or from the previous analysis. And this comes from a Lillis et al. Or the reason why we chose these is that Lillis et al. In 2013 provided estimates for these craters. So we have the age and the era sort of from oldest to newest. Specific for Henry, that was outside of that work. So we looked at crater density estimates with some colleagues, and that pegged a very accurate estimate about 3.6 gigaNMs a billion years ago. And we assigned magnetization ratings to all of these craters. And if we kind of take again, -3 meaning strong demagnetization, 3 meaning strong remagnetization. And if we kind of sort age and magnetic rating and compare the two, we see a strong demarcation around formation of Huygens crater. And if we kind of plot this going from oldest to newest, again, magnetization rating, we see that we kind of get an estimate for when the dynamo died, because before we have strongly magnetized craters, afterwards we have strongly demagnetized craters. And so in kind of going back to that plot, we see the dynamo cessation estimate is fairly around 3.9 gigaNMs, but as late as 3.6 for Henry crater. And so to kind of put that in context with other works, this work is, it falls into the range of Miedelholtz and extends some of the prior works where they ended, and it puts a definite end at 3.6 gigaNMs for Henry crater. In terms of magnetization depth, we sort of started answering this before. Recall that magnetization depth is shallow and deep. We've kind of gotten evidence for both of these. For deep magnetization, we found not many craters were demagnetized, greater than 150 kilometers. But on the other hand, we have these handful of compelling examples like Henry and Kowalski, which are much smaller than the expected range, but exhibit strong magnetization. So the fundamental question is, why are we having some craters and not others? So far, we've only spoken about impact-induced demagnetization. We want to kind of constrain this, and we want to talk about radiogenic heat-producing elements in the lithosphere, which are going to, as you go deeper, eventually you're going to get to something called Curie depth, where it's so hot that no magnetization can exist. And if there's impact-induced demagnetization, the sweet spot, we'll find it right here. And so kind of calculating this, first we get a location from the GRS maps of these radiogenic heat producing elements. We calculate total heat flow in this region. QC is crustal heat flow from these heat producing elements. This will be a function of temperature and a function of time and position, specifically around that crater. And for basal heat flow, this will be just a parameter sweep from about 0 to 50, depending on, because we don't know how active the mantle was at the time of the formation of, let's say, Henry crater. So we're just doing a parameter sweep. It's a simple calculation after that, assuming a linear crust. And then we get this kind of Curie depth at Henry crater, plot of temperature versus depth that we can use to estimate. And so this is kind of where the future work goes. Further estimate. So we have a lower estimate or lower bound. We want a higher bound after that in terms of, we're going to use ISIL 2D impact modeling to see pressure versus depth to find a range for demagnetization. We're going to hopefully use some spherical harmonic analysis techniques to come up with a power spectrum to see where the actual data estimates of demagnetization is, and hopefully look at some other things. So Arabia Terre is a region of high possible groundwater activity. There's no magnetic anomalies, but open to other interpretations. And of course, thanks to my advisor and Altunkaya for their help. Thank you.
Questions? Come on up.
Hello, thank you for your talk. I have a question about the heat flow determination that you have in mind to do. You mentioned this is for the basal heat flow, but and I saw your equations. Are you trying to also consider radiogenic heat in this determination?
Yeah, so the total heat flow at a certain location, which we're going to use to go into our temperature versus depth calculation later on, that's just going to be the sum of crustal heat flow due to radiogenic heat producing elements plus the basal heat flow.
Okay, thank you.
There was a question on the chat related to the Henry crater. It's asking, the yellow track is quite different from the other tracks.
Sorry, you said?
Yeah, so the yellow track's quite different from the other tracks. No reduced magnetization. Why could this be?
In general, for MAVEN, for these cross-sectional plots, even though we're looking at nighttime data, there tends to be, I showed kind of the prettier plots in this example, but a lot of the plots do show a lot of disagreement and incoherence. Some of these we chalk up to being from a higher altitude, which is why we discriminate or we plot each track with a certain color so we could correspond to altitude. But other times we're just not sure why that is. So hopefully spherical harmonic modeling techniques can give us a more comprehensive picture of the crater at a certain time. But other than that, I'm not too sure about the specifics of MAVEN inconsistencies.
Thank you very much.
Cool. Thank you.
And with that, I believe we conclude our session. Thank you to all our speakers.